What are some numbers associated with tire pressure?
Tire pressure is measured using a tire pressure gauge, with the most common measuring device being about the size of a pen. First, a bit about pressure. The atmosphere at the surface of our planet measures about 14.7 pounds. 6.67 kilograms per square inch, or a 1 inch, 2.54 centimeters, square column of air weighs 14.7 pounds. This changes depending on the altitude. For example, at an altitude of 10,000 feet, 3,048 meters, the air pressure decreases to 10.2 pounds, 4.63 kilograms, per square inch. But a car, truck, SUV, or bike tire needs more pressure in order to inflate. By increasing the number of atoms inside the tire, there are more collisions between the atoms and more pressure exerted on the sides of the tire. In other words, a pump stuffs more air into a constant volume. The confines of the tire, so the air pressure within the tire rises. A car tire's pressure is typically at about 30 pounds, 13.61 kilograms, per square inch. A bicycle tire's pressure can be around 90 pounds, 40.82 kilograms, per square inch.
How are modeling and simulation used in engineering?
Modeling and simulation have become an essential part of engineering on both a small and large scale. Because building any size of structure takes time and money, engineers often develop a mathematical model, a set of equations that describe what may happen to a structure if it is built the way it is represented by the model. Using a computer, or graphic, representation gives the engineers a three-dimensional view. For example, before the space shuttle was built, engineers used mathematical modeling to simulate what the craft would look like in 3 dimensions. In this way, the engineers learned how the shuttle would fly, how strong the heat-resistant tiles had to be in order to re-enter the Earth's atmosphere, and even how to maneuver the shuttle under various conditions as it landed. The computer was the only way to solve such problems without real-life testing. It quickly and easily solved a plethora of mathematical equations, especially calculus and differential equations that represented how the shuttle would take off, fly, and land.
What is accuracy in measurement?
Accuracy in measurement is based on relative error and number of significant digits. Relative error is the absolute error divided by the calculated, or estimated, value. For example, if a person expects to spend $10 per week at the local espresso bar, but he or she actually spends $12.50, the absolute error is 12.50. 10.00 equals 2.50, the relative error then becomes 2.50/10 equals 0.25, to find out the percent, multiply by 100, or 0.25x 100 equals 25% of the original estimate. Significant digits refers to a certain decimal place that determines the amount of rounding off to take place in the measurement. In most cases, this means that there are more numbers to the right of the decimal point. But beware. Accuracy in measurement does not mean the actual measurement taken was accurate. It only means that if there are a large number of significant digits, or if the relative error is low, the measurement is more accurate.
What are the base SI units?
There are several base units at the heart of the international system, SI. The following lists the 7 base units: meter, distance, kilogram, mass, related to weight, second, time. Ampere, electric current, Kelvin, temperature, mole, amount of substance, candela, intensity of light. Still other SI units called SI-derived units are defined algebraically in terms of the above fundamental units. All the base units are consistent with the metric system called the MKS or MKS system, which stands for meter, kilogram, and second. Another metric system is the CGS, or CGS, system, which stands for centimeter, gram, and second.
What are the odds when playing craps?
Craps is probably the most popular game of chance in the world. It is also illegal to play in many places. But it has a long history. It was played in ancient Greece and Rome and was even a mainstay of some old 1930s and 40s movies. Craps can be played using a wall and a pair of dice. It is a popular casino game in places such as Las Vegas and even on the internet, with betting on craps involving a complex equation. Its popularity no doubt comes from its simplicity. In craps, a player throws 2 dice, their number, roll, is the total of the dots on the top faces of the dice. If the initial roll is a 7 or 11, called a natural, the player wins. If the number 2, 3, or 12 comes up called craps, the player loses, but keeps the dice. If the sum of the dice adds up to the number 4, 5, 6, 8, 9, or 10, that number becomes the thrower's point. The player then continues to shoot until he or she throws the point number again, in which case the gambler wins and retains the dice. But if the player shoots a sum of 7 before he or she can roll the point value, he or she loses and gives the dice to the next player. Craps is truly a game of chance, with the probability mathematics of craps fairly straightforward. For example, take the probability of winning on a roll-by-roll basis, in which P equals n, is the probability of rolling a point n. The resulting numbers show that the probability of winning is 244/495. Or the shooter wins about 49.2929% of the time.
How can word problems be expressed as equations?
There seem to be a gazillion word problems out there. Just ask anyone taking such tests in grade or high school. The one thing most have in common is that they can be expressed as an equation, many as algebraic equations in which there are known and unknown quantities. In almost all instances, there are keywords that lead the reader to determine not only the numbers and variables, but also what operations to use in the equation to determine the answer.
What does the greatest common factor mean?
The greatest common factor, or GCF, sometimes called highest common factor, of two whole numbers is the largest whole number that is a factor of both. Take, for example, the numbers 12 and 15, the factors of 12 are 1, 2, 3, 4, 6, and 12, the factors of 15 are 1, 3, 5, and 15. Therefore, the common factors or numbers in both lists of factors are 1 and 3, and the greatest highest common factor in this case is 3. There is another method used to discover the GCF. Listing the numbers' prime factors, then multiplying those numbers. For example, the prime factorizations of 12 and 15 are 2x 2x3 equals 12 and 3x5 equals 15. Notice that the prime numbers have 3 in common, thus, the GCF is 3. An example with larger numbers is to find the GCF of 36 and 54. Working it out by the first method. The factors of 36 are 1, 2, 3, 4, 6, 9, 12, 18, and 36. The factors of 54 are 1, 2, 3, 6, 9, 18, 27, and 54. The greatest, or highest, common factor of both numbers is to work it out using prime factorization. The prime factorization of 36 is 2x 2x 3x 3, the prime factorization of 54 is 2x 3x 3x 3. Both these factorizations have 1 2 and 2 3's in common. Thus, we multiply those common numbers, or 2x 3x 3 equals 18.
What is the universal gas law?
The universal gas law, also called the universal gas constant or the perfect gas law, is a chemical law that can also be looked at mathematically. It is represented by the equation PV equals nRT, in which P is pressure, V is volume, N is the number of moles of gas, R is the gas constant, and T is the temperature in Kelvin. For more about the Kelvin temperature scale, see Mathematics Throughout History.
What was the progression of logarithm development?
The invention of logarithms was a long process, starting with Scottish mathematician John Napier. 1550 to 1617, also known as Laird of Merchiston, who first came up with the idea of logarithms in 1594. But the actual invention and announcement of logarithms would take another 20 years. In 1614, Napier would publish Mirifici Logarithmorum Canonis Descripto. Description of the wonderful canon of logarithms, which offered tables and rules for their use. Not long afterward, in 1617, English mathematician Henry Briggs 1561 to 1630, published Logarithmorum Cilias Prima, logarithms of numbers from 1 to 1000. Introducing the concept of common logarithms or logarithms based on the powers of 10. And finally, independently from Briggs and Napier, came Swiss mathematician Just Bürgi, 1552 to 1632. Who in 1620 presented Arithmetisque und Geometrische Progresstabulum, a German work presenting the discovery of logarithms. These discoveries differed in several ways. Napier's approach was algebraic, Bürgi's was geometric. There were differences from the common and natural logarithms we use today. And neither Napier nor Bürgi mentioned the concept of a logarithmic base, something that Briggs presented. By 1624 Briggs would write Arithmetica Logarithmica, the arithmetic of logarithms, extending his common log tables from 1 to 20,000 and from 90,000 to 100,000. But the work on logarithms did not end with Napier. Briggs, or Bürgi. Natural logarithms eventually evolved out of Napier's original work. Defining logarithms as exponents was finally recognized by English mathematician John Wallis. 1616 to 1703, who presented them in his 1685 publication, De Algebra Tractatus, Treatise of Algebra.
The following lists some simple keywords and their corresponding operation. What are independent and dependent variables in algebra?
Variables can be broken down into independent and dependent variables. An independent variable is a quantity that increases or decreases. Is variable, or that has an infinite number of values in the same expression. For example, in the expression x2 plus y2 equals r2, x and y are variables. A dependent variable is a quantity that varies but is produced by changes in the independent variable. In other words, the dependent variable's value is dependent on the independent variable. For example, in the expression f, x, equals y, x is the independent variable and y is a dependent variable. Because y is dependent on the value of x.
Who invented matrices?
Although a simple form of matrices may have been used by the Mayans, and maybe other cultures. See below, the true mathematical use of a matrix was first formulated. Around 1850 by English mathematician, poet, and musician James Sylvester, 1814 to 1897. In his 1850 paper, Sylvester wrote, "For this purpose we must commence, not with a square, but with an oblong arrangement of terms consisting, suppose, of m lines and n columns. This will not in itself represent a determinant, but is, as it were, a matrix out of which we may form various systems of determinants by fixing upon a number p, and selecting at will p lines and p columns, the squares corresponding of pth order." In this case, Sylvester used the term matrix to describe its conventional use, or the place from which something else originates. But the matrix story was not all about Sylvester. In 1845 Sylvester's collaborator, English mathematician Arthur Cayley, 1821 to 1895, used a form of matrices in his work on the theory of linear transformations. By 1855 and 1858, Cayley began to use the term matrix in its modern mathematical sense. Although he was an avid mountaineer and a lawyer for close to a decade and a half, which is how he met Sylvester, during his free time Cayley published more than 200 mathematical papers. He also contributed a great deal to the field of algebra, initiated analytic geometry of n-dimensional spaces, and developed the theory of invariance, among other mathematical feats. Sylvester also remained brilliant throughout his life. He founded the American Journal of Mathematics in 1878, and at the ripe age of 71, he invented the theory of reciprocance, differential invariance.
Who invented the symbol for zero?
Although the Babylonians determined there to be an empty space in their numbers, they did not have a symbol for zero. Archaeologists believe that a crude symbol for zero was invented either in Indochina or India around the 7th century and by the Mayans independently about 100 years earlier.
What is sociology?
Sociology is the study and classification of human societies. It delves into the relationships among peoples mostly within, but also outside, each culture. Sociology studies are based on the idea that behavior of peoples is influenced by social, political, occupational, and intellectual groupings. It is also based on the immediate and particular settings in which individuals reside.
What is a partial derivative?
Partial derivatives, seen written as the symbol a, are derivatives of a function containing multiple variables that have all but the variable of interest held fixed during the differentiation. Thus, when a function f, x, y, depends on more than one variable. The partial derivative can be used to specify the derivative with respect to one or more variables. There are other terms, too. Partial derivatives that involve more than one variable are called mixed partial derivatives. And a differential equation expressing one or more quantities in terms of partial derivatives is called, logically, a partial differential equation. These equations are well known in physics and engineering, and most are notoriously difficult to solve.
How can one visualize Pascal's triangle using algebra?
One way of looking at Pascal's triangle is through its connection to algebra. For example, expand, or remove the brackets around, the expression, 1 plus x, 2 equals, 1 plus x, 1 plus x equals 1 plus 2x plus x2. The same can be done with a cube, for example, 1 plus x, 3 equals, 1 plus x, 1 plus x, 1 plus x, equals, 1 plus x. 1 plus 2x plus x2, equals 1 plus 3x plus 3x2 plus x3, and even the expression, 1 plus x, 4, which equals 1 plus 4x plus 6x2 plus 4x3 plus x4. The coefficients. The numbers in front of the x's, in the results are the connection. For the first example, the coefficients are 1, 2, 1, for the second one, 1, 3, 3, 1, and for the last expression, the coefficients are 1, 4, 6, 4, 1. These, of course, are the third, fourth, and fifth lines from Pascal's triangle.
What does it mean if a set is countable?
If a set is countable, or denumerable, it means that it is finite. This also means that the set's members can be matched in a one-to-one correspondence in which each element in one set is matched exactly with one element in the second. And vice versa with all the natural numbers, or with a subset of the natural numbers. Mathematicians often say, A and B are in one-to-one correspondence, or A and B are bijective. For more about one-to-one correspondence, see Math Basics. In set theory, all finite sets are considered to be countable, as are all subsets of the natural numbers and integers. But sets such as real numbers, points on a line, and complex numbers are not countable.
What is a matrix?
A matrix is a concise way of representing and working with linear transformations, also. It is a rectangular array or grid of numbers or variables that allows the user to perform certain mathematical operations. They are usually symbolized as large parentheses or two large pair of Parallel double lines surrounding the array of numbers or variables. These numbers can be manipulated to solve systems of equations or problems with many different variables or numbers by addition, subtraction, multiplication, or other methods. Each row and column of a given matrix must have the same number of elements. Anytime one has a list of numbers, or a table of numbers in a specific order. Concerning anything at all, prices, grades, populations, coordinates of points. Production tables, it can be considered to be a matrix. When the idea of the matrix was first conceived, its development dealt with transformation of geometric objects and solution of systems of linear equations. Historically, the early emphasis was on the determinant, see below, not the matrix. Today, especially in linear algebra, matrices are considered first.
What do we know about Babylonian mathematical tables?
Archaeologists know that the Babylonians invented tables to represent various mathematical calculations. Evidence comes from two tables found in 1854 at Sankara on the Euphrates River, dating from 2000 BCE. One listed the squares of numbers up to 59, and the other the cubes of numbers up to 32. The Babylonians also used a method of division based on tables and the equation a/b equals ax, 1/b. With this equation, all that was necessary was a table of reciprocals, thus the discovery of tables with reciprocals of numbers up to several billion. They also constructed tables for the equation n3 plus n2 in order to solve certain cubic equations. For example, in the equation x3 plus bx2 equals c, note, this is in our modern algebraic notation. The Babylonians had their own symbols for such an equation. They would multiply the equation by a 2, then divide it by b3 to get x/b, 3 plus x/b, 2 equals ca2/b3. If y equals x/b, then y3 plus y2 equals ca2/b3, which could now be solved by looking up the n3 plus n2 table for the value of n that satisfies n3 plus n2 equals ca2/b3. When a solution was found for y, then x was found by x equals by/a. And the Babylonians did all this without the knowledge of algebra or the notations we are familiar with today.
What are the addition rules of probability?
In probability theory, the addition rule is used to determine the probability of events A or B occurring. The notation is most commonly seen in terms of sets, P, AUB, equals P, A, plus P, B, P, AB, in which P, A, represents the probability that event A will occur, P, B, represents the probability that event B will occur. And P, AUB, is translated as the probability that event A or event B will occur. For example, if we wanted to find the probability of drawing a queen, A or a diamond, b, from a card deck in a single draw, and since we know there are 4 queens and 13 diamond cards in the deck of 52, the equation and resulting probability becomes 4 50-seconds plus 13 50-seconds. 1 50-second equals 16 50-seconds. The 1 50-second is derived by multiplying 4 50-seconds x 13 50-seconds. But there are also rules of addition for mutually exclusive and independent events. For mutually exclusive events, or events that can't occur together, the addition rule reduces to p, AUB, equals p, A, plus p, B. For independent events, or those that have no influence on each other, the addition rule reduces to p, AUB, equals p, A, plus p, B, p, A, p, B.
What is a polyhedron?
The word polyhedron comes from the Greek poly, meaning many, and the Indo-European word hedron, meaning seed. In geometry, a polyhedron is considered to be a three-dimensional solid that represents the union of polygonal regions, usually joined at their edges and having no gaps. Polyhedrons are classified as convex, or if you extend any side, the figure lies on only one side of the plane. For example, a pyramid and cube, a concave polyhedron is one that can extend on both sides of such a plane. For example, a form that exhibits concavity on one or all sides of the polyhedron. The plural of polyhedron is often seen as polyhedrons, but it is more correct to use polyhedra.
What is the area of a two-dimensional geometric figure?
The area of two-dimensional figures varies depending on the object. For the simpler two-dimensional figures, square, rectangle, parallelogram, the area can actually be found by calculating the number of square units in the interior of the object. Such a task can be difficult and time-consuming, so mathematicians simply multiply the height, h, times the base, b, sometimes said as length times height or length times width, with rectangles. For more information about the area of geometric figures, see the Appendix 3, Common Formulas for Calculating Areas and Volumes of Shapes.
Why are arcs and angles important to circles?
Everything starts with the angle whose vertex is at the center of the circle. Logically called the central angle of a circle. All the central angles of a circle add up to 360 degrees. Every central angle cuts the circle into two arcs, the minor arc, always less than 180 degrees, and the major arc, always more than 180 degrees. Thus, the measure of the minor arc is actually the measurement of the central angle. while the measurement of the major arc is 360 degrees minus the measure of the central angle. An arc length is the distance between an arc's endpoints along the path of the circle. Congruent arcs are arcs with the same measurements. When the diameter of a circle separates the circle into two congruent arcs, it is called a semicircle.
What is a random walk?
Although one might think of a random walk as one that a person takes on the spur of the moment in a part of town he has never walked before, it means something totally different in probability theory. A random walk is a random process made up of a discrete sequence of steps, all of a fixed length. For example, in physics, the collisions of molecules in a gas are considered a random walk that are responsible for diffusion. The number of permutations is the number of different ways specific entities within the cat group can be arranged, with the positions being important.
Can there be more than one type of number?
Yes, numbers can be classified as more than one type, and it's not always easy to keep them straight. The following lists some ways to better understand the plethora of number types. A rational number is not always an integer. 4/1 is an integer, but 2/3 is not. But an integer is always a rational number because it can be represented by a fraction by putting the integer over 1, or /1, such as 2/1 or 234/1. A number can either be rational or irrational, but not both. The number for pi, 3.141592, is irrational, the decimal does not repeat, and real 0.
Can there ever truly be a balance in supply and demand?
As most people know from the fluctuating prices of gas, food, and other staples, and thanks to the ever-changing variables in the mix such as war and natural disasters, there is rarely, if ever, a good balance between supply and demand.
Are there different types of infinity in mathematics?
To most of us, the universe represents infinity. But in mathematics it is the unbounded quantity that is greater than every real number. Called potential infinity in mathematics, it is the potential for infinity that exists with natural numbers, because one can always conceive of a number greater than any given number. Another type of infinity in mathematics is completed infinity, which refers to the size of an infinite set, such as all the points on a line. At the end of the 19th century, German mathematician Georg Ferdinand Ludwig Philipp Cantor, 1845 to 1918, showed that different orders of infinity existed, and that the infinity of points on a line was of a greater order than that of prime numbers.
What is symbolic logic?
Symbolic logic, also called formal logic, is mainly concerned with the structure of reasoning. It determines the meaning and relationship of statements used to represent specific mathematical concepts and provides a means to compose proofs of statements. Symbolic logic draws most notably on set theory. It uses variables combined by operations such as not or and assigns symbols to them, and, respectively.
Do numbers continue into infinity?
When most of us think of infinity, we envision the universe continuing on forever. And in mathematics, we often think of numbers that are never-ending. Sometimes it is difficult to understand infinity. Since our own lives and most of our experiences are finite, they eventually end. Infinity is a mind-boggling concept. There are several rules to mathematical infinity. The three most important are, no matter how high you count numbers, you can always count higher. No matter what length you draw parallel lines, they will never meet, and when starting with a line, dividing it in half, then dividing that in half, and so on, you will never stop dividing the resulting line segment. Even though scientists and mathematicians agree that infinity exists theoretically, it is often a difficult concept to understand and accept.
What does this mean for our calendar?
It is already known that our calendar and the length of a year were only off by 24 seconds. 0.00028 days, in 1582, a very small discrepancy that will eventually be noticed. But when you add in the slowing down of the Earth's rotation, it will make the year even shorter. In fact, since 1582, the year has decreased from 365.24222 days to 365.24219 days. Or an actual decline of about 2.5 seconds.
What were some of the contributions by the Arab world to mathematics?
From about 700 to 1300, the Islamic culture was one of the most advanced civilizations in the West. The contributions of Arabic scholars to mathematics were helped not only by their contact with so many other cultures, mainly from India and China, but also because of the Islamic Empire's unifying, dominant Arabic language. Using knowledge from the Greeks, Arabian mathematics grew. The introduction of Indian numerals, often called Arabic numerals, also helped with mathematical calculations.
What are some characteristics of numerical analysis methods?
Characteristics of numerical analysis methods include accuracy. The numerical approximation should be as accurate as possible. Robustness. The algorithm should be able to solve many problems and should relate to the user when the results are inaccurate, and speed. The faster the computation, the better the method.
What is the Pauli exclusion principle?
Quantum theory also relies on the Pauli exclusion principle. This principle, developed by Austrian-born Swiss physicist Wolfgang Pauli, 1900 to 1958. In 1925, states that two particles of a certain class called fermions, and otherwise known as electrons, neutrons, and protons can never be in the same energy state. For example, two electrons with the same quantum number can't occupy the same atom.
Is math used to describe the strength of materials?
Materials science is also a major part of engineering, and includes a great deal of mathematics. For example, engineers need to know how materials stand up to stress and strain from the pressure of either a structure or overlying materials. A basic understanding of how structures respond to the action of forces and how these forces affect the performance of various building materials, such as wood, steel, concrete, and so on, is essential.
Why are the terms cardinal and ordinal sometimes confused in mathematics?
Cardinal and ordinal numbers are sometimes confused because they have two distinct mathematical definitions. The cardinal numbers in the numbering system should not be confused with cardinal numbers in set theory, in which any method of counting sets using a cardinal number gives the same result. Likewise, the ordinal numbers in arithmetic should not be confused with ordinal numbers in set theory. Such numbers, often called ordinals for short, are the order type of a well-ordered set. They are divided into two types, finite and transfinite ordinals. For more about sets, ordinals, and cardinal numbers, see Foundations of Mathematics.
How do you expand logarithms?
Like an algebraic expression, it is possible to expand logarithms, which is a way of picking apart an expression. The following lists two examples of expanding a logarithmic expression. To expand log 2, 3x, equals log 2, 3, plus log 2, x, to expand log 2, 12/x, equals log 2, 12, log 2, x.
What does E represent in terms of logarithms?
No, E is not the code name in a James Bond movie. When talking about logarithms, or logs. In the majority of mathematical circles, it means the base of the natural logarithm.